continuous random variables and probability distribution. So far, we talked about discrete random variables. Now we are moving to continuous random variables. Suppose X is a continuous random variable. Then a probability distribution or probability density function, PDF, of variable X is a function like f of X such that for any two numbers A and B, when A is less than equals to B, the probability that X is bounded between A and B inclusive is the definite integral from A to B of f of X dx. So the probability that X takes a value in the interval A to B is the area above the interval and under the graph of the density function. And we can visualize it just right here. The graph of f of X is usually referred to as the density curve. So suppose X is a continuous random variable. If there is a non-negative function f of X defined for all real X values between negative infinity to positive infinity, having the properties that for any set like B of real numbers, the probability that X belongs to that set is the integral of f of X dx over B, then the function f of X is called the probability density function of the random variable X. In words, we state the probability that X be in set B obtained by integrating the probability density function over the set B. Some notes from calculus. The probability that X belongs to the set, which is basically real numbers, negative infinity to positive infinity, is the integral of f of X dx. The lower bound is negative infinity, and the upper bound is positive infinity. And as you know, it is equal to 100% or 1. If you're interested in calculating the probability that X is exactly A, you're basically calculating the definite integral of f of X when the lower bound and upper bound both are equal to A and is equal to 0. The cumulative distribution function f of X for a continuous random variable X is defined for every number X as f of X, which is the probability that X is less than equals to X, which can be defined as the integral of f of Y dy, and Y ranges between negative infinity to X. For each X, f of X is basically the area under the density curve for the left-hand side of X values. We can visualize both the cumulative density function and also looking at the density curve. This is the graph of f of X. And on the right-hand side, you have the graph of cumulative density function. So as we mentioned, the cumulative distribution function f of X for a continuous random variable X is defined for every number X as the integral of f of Y dy, negative infinity to X, which is the range for your variable Y. Suppose X is a continuous random variable with probability density function of f of X and cumulative density function capital F of X. Then for any number A, the probability that X is more than A is 1 minus f of A. And for any two numbers A and B, When a is less than b, the probability that x is bounded between a and b inclusive is f of b minus f of a. From calculus, recall that if x is a continuous random variable with probability density function f of x and cumulative density or distribution function f of x, then at every x at which the derivative of f exists, f prime is equal to f. So the derivative of cumulative distribution function is equal to the probability density function. Very good. The direction of an imperfection with respect to a reference line on a circular object, such as tire, brake rotor, or flywheel, is often subject to uncertainty. Consider the reference line connecting the valve stem on a tire to the center point, and x be the angle measured clockwise to the location of an imperfection. One possible probability density function for x is f of x equals to, when x is bounded between 0 and 360 degrees, 1 over 360. Well, you can easily visualize this graph. This is just a straight line when x is bounded between 0 and 360. Everywhere else, it is going to be just the line, as you can see right here. Now, if I ask you to calculate the probability that the angle is bounded between 90 and 180 degrees, what you're going to do, you're going to basically follow the formula, calculate the definite integral of the function, which is 1 over 360. This is x divided by 360. X is bounded between 90 and 180, which gives you 1/4 or 25%. So basically, when you're looking at the probability that x is bounded between 90 and 180, you're finding this shaded region or shaded area. The probability that the angle of occurrence is within 90 degrees of the reference line is the probability that x is bounded between 0 degrees and 90 degrees plus the probability that x is bounded between 270 degrees and 360 degrees. It is 25% plus, if we do the calculation for 270 and 360, we get 25% again. If you add this together, it is 50%. So it's basic calculation. We have a constant function, and then we plug in the constant function into the integral, into the definite integral, and do the calculation. That way, we can easily calculate the probability that x is bounded between two values. And please note that you have a continuous random variable. One interesting case is a uniform random variable. X is a uniform random variable on interval alpha and beta if its probability density function is given by f of x, which is defined as if x is bounded between alpha and beta, the function is 1 over beta minus alpha, and everywhere else it is 0. To calculate the cumulative distribution function of a random variable of uniformly distribution over interval alpha to beta, we know that f of a is equal to integral of f of x dx when x is bounded between -infinity and a. This is the area to the left-hand side. So f of a can be calculated as when alpha is more than equals to a, or as a is less than equals to alpha, you have 0. When a is bounded between alpha and beta, you have a minus alpha divided by beta minus alpha. And for any other value more than equals to beta, you get 1.